lecture 16 of our series on numerical methods in civil engineering, we are going to talk about arc length and gradient based methods. If you recall, in our last lecture, probably in our last two lectures, we have looked at various methods for solving nonlinear equations, and the methods we concentrated on first was the most well known method, the Newton-Raphson method, and then we looked at variations of the Newton-Raphson method, modified Newton, and finally we looked at quasi-Newton, right. However, it is not always possible to solve all the problems that one encounters in civil engineering applications with nonlinearities using the Newton-Raphson method. Why? Well, because our load path, unless it is really well behaved, the Newton-Raphson method cannot converge, and we will see examples of why that happens. In many structure and solid mechanics problems, the load displacement curve changes slope. For instance, here I have plotted a load displacement curve with a red line, that's my load displacement curve, and you can see that it is changing slope. It is positive up to here. Here probably the slope goes to 0, it changes sign, right. Same thing happens here, right. So this will happen in a structural mechanics application, for instance, when we have a load limit point, right, where we reach a maximum value of the load, right. The structure cannot take any more load, that is the maximum load that it can carry. After that there is softening, or the load falls, load decreases with increasing displacement, right. So that is a load limit point. So when we use Newton-Raphson method for solving such a problem, we encounter difficulties. This is because the equilibrium path following algorithm adopted so far, namely the Newton-Raphson method, moves from one equilibrium state to the next equilibrium state based on the tangent stiffness, that is evaluated at the converged equilibrium state, at the previously converged equilibrium state, right. We evaluate the tangent stiffness, then march along that direction in n-dimensional space. If the slope undergoes large changes along the equilibrium path, it is necessary that A, the orientation of the path be correct, and B, step sizes along the path be controlled. For instance, if we have a situation like this where we obviously have a limit point and we are moving along this direction along the load displacement curve, we took this initial increment delta u0 and we are evaluating the tangent here, and you can see if the tangent here points in this direction, then the next displacement increment will ask me to travel in this direction in load displacement space, which is totally wrong, right. It should actually be traveling in this direction, right. So it may be necessary to check the orientation. Also, the step size may need to be scaled. For instance, if we typically have softening behavior, softening meaning that even though the displacement increases, the load actually decreases, right. In a situation like this, again, if we reach a point here, right, if we reach a limit point like this, and then if we calculate the tangent here, that is pointing in this direction. So how do I calculate my incremental displacement? I invert my tangent stiffness, multiply it, take the product of the inverse of the tangent stiffness with my load increment, and that gives me my incremental displacement. So this is my load increment from here to here. This is my load increment, this is my slope, this is my tangent stiffness. So this tells me, if I divide the load increment by the tangent stiffness, let's think of 1D, so let's talk about division, right. If we think of that, then that tells me that I must move from here to here on the displacement axis. But once it moves here, you can see that the structure cannot respond because the load displacement curve is like this, right. So it cannot calculate an internal force to equilibrate the applied load, and then the problem diverges, it cannot converge, right. So if I have a situation like that, one solution is to scale the displacement increment, or maybe even the load increment. So I have got my initial displacement increment and load increment is suppose delta u star and delta f star. So I say no, I can't take that bigger load or that bigger displacement. So, let me scale it by a factor eta, right. If I do that, I will probably end up with some point here where there is a load a response, right, where there is a valid response for the structure, where there is the internal force is not undefined, right. So, I have a chance of reaching equilibrium, right. So, that is the simplest possible thing that we can do, that is control the load step and the displacement step. So, up till now Newton-Raphson we have so we are controlling the load step and the displacement step. So, that brings us to a new concept which is known as the arc length type methods, right. Let us look at what these are. Arc length methods are based on the idea that the combined displacement and load increment should be controlled during equilibrium iterations. So, not just the load, not in a load driven problem we control the load, in a displacement driven problem we control the displacement, but in this case we are controlling both the load and the displacement. We are saying that neither the displacement increment nor the load increment should exceed certain cutoff values during the equilibrium iterations. This will help the problem to converge. This will help my nonlinear iterations to converge. So, they are based on the idea that the combined load displacement increment should be controlled. So, how is that done? Well, we take an initial load and displacement increment from an equilibrium state. So, suppose I have an equilibrated state with displacement u0 and force F0. I calculated incremental force delta F, apply an incremental force delta F, right, and then I calculate an incremental displacement delta u0 using my tangent stiffness at u0 f0, right. So, but that just gives me the first step in my iteration, but following that the equilibrium iterations are restricted to a constrained surface in the combined load displacement space. So, let me show a picture and this will probably help you to understand this. So, this is my equilibrated state u0 f0, right, and from here I have taken an initial increment delta u1 delta f1. How did I calculate this? I got my delta f1 which was my force increment, I took my tangent stiffness here, I inverted my tangent stiffness, took the product with delta f1 and got my delta u1, but this is obviously does not an equilibrated state, right. So, I have what will be an equilibrated state? A point that must lie on my red curve, right, where my internal force is going to be equal to my external force. So, what do I do? Well, I say that I take a step from here to here, this is my trial step, right, it is like my predictor, this is what I predict it to be. These concepts are common to lots of numerical methods, but basically the idea is I take an initial predictor and then I take a corrector, I correct it to reach the red line which is my desired solution, but I don't do my correctors are constrained, right. Why are they constrained? Well, it says that the correctors that I must take to move from this point to this point to this point, my equilibrated solution, right, my equilibrated solution must move along this curve, right. This is my constraint curve. So, I can only move from here to here by traveling along this arc, right. So, that is why they are known as arc length methods, right. So, I am moving from here to here by traveling along that curve, and this curve is a surface in the load displacement space, right. I have this is just a 2D idealization. So, I am basically a hyperplane, right, or some surface, multidimensional surface in multidimensional space, and I have to move along that surface from my initial predicted solution to my equilibrated solution. So, after the initial load and displacement increment from an equilibrium state, the equilibrium iterations are restricted to a constrained surface in the combined load and load displacement space. The next equilibrium state occurs at the intersection of the equilibrium path with the constrained surface. It occurs at the intersection of the equilibrium path with the constrained surface. It occurs right here. So, this is my equilibrium path, this is my constrained surface, this is my new equilibrated state. In the first iteration of an increment, the displacement is determined from a load increment by the usual linearized stiffness matrix, right. That is how I determine my delta u1 from here, right. I know delta f1, I know the tangent, I can calculate delta u1. This is followed by simultaneous combined displacement and load sub increments. So, following that initial increment, when my load is fixed, delta f1, my load increment is fixed and I calculate my displacement increment. Now, in the subsequent iterations, I can change both my load and my displacement. You can see obviously that if I have to travel from here to here, I have to change both the load and the displacement, right. So, I have to change both my load and displacement in order to reach this point on the this intersection point. So, this is followed by simultaneous combined displacement and load sub increments delta ui, delta fi, where these are the I refers to the iteration counter, right. I keep on iterating, after which after each iteration I update my incremental displacement and my incremental loads until I finally reach my converged state. So, delta ui equal to delta ui minus 1 plus increment in ui, delta fi equal to delta fi minus 1 plus increment in fi. So, I have going from here to here in these little iteration steps which are denoted by I. Iterations, sorry. So, let u0 f0 denote the last established equilibrium state. So, I am just going through this in somewhat more detail. We impose a load increment delta f, then we calculate the displacement increment delta u is equal to k inverse of delta f. In the subsequent iterative procedure, the load magnitude is adjusted via a scalar parameter xi, while the relative magnitude of the individual load increments are retained. What does it mean? Well, I know my load increment delta f, right. This is what I am controlling, right. So, this it's a load control problem. I am prescribing delta f. I am increasing the load by delta f, but that delta f is a vector, right. It has got many components, right. So, how am I going to scale that delta f? How am I going to scale that delta f to bring it to my converged state? Well, the way I am going to scale it is that I am going to change the magnitude, right. I am just going to keep all the components, the direction the same, right. I am going to keep the direction of the load vector the same. I am just going to scale its magnitude. So, this factor xi, this parameter xi, it scales the magnitude of the load vector, but it leaves the directions unchanged, the direction of the load vector unchanged, right. So, the ratio between the load components remains the same, it is only the magnitude that is changed. So, an iterative procedure is constructed from the residual force like this. So, basically we say that the residual is equal to F minus Gu, which we have seen many times before, right. So, by applied load, this is my response internal force, and this I am going to write as F0 plus xi times delta F. F0 was my last equilibrated load, right. Delta F is my initial increment and xi is my scalar parameter with which I am going to scale that load increment. So, F0 plus xi delta F must be equal to F0 plus xi delta F minus my internal force, my response, which is a function of the initial displacement u0 plus my increment delta u, is going to, whatever the difference is, that is going to be my residual, right. That is going to be my residual, and I am going to write this as xi delta f minus delta g. Why? Because I am going to write minus g u0 plus delta u as g u0 plus delta g. So, I am just representing g u0 plus delta u as g of u0, right, the internal force at displacement u0 plus the increment in the internal force delta g. So, and this g of u0 must be equal to f0 because the 0 is an equilibrated state, right. f0 must be equal to g of u0. So, f0 cancels with g of f u0 and I have xi delta f minus delta g, right. So, that is going to be my residual. In addition, we have a constraint equation which relates the current displacement increment delta u to the current load increment xi of delta f, right. So, my current displacement increment is delta u, right, it is this thing, right, and my current load increment is xi of delta f, and I am saying that this delta u and this xi of delta f, the displacement increment and the load increment cannot be arbitrary, they must lie on the constraint surface, that is they must satisfy this constraint equation. This constraint equation is a function of delta u and psi of delta f, right. So, these increments must satisfy that equation. So, now we have two equations, right, we have a coupled system. We have one equation right there which is my residual, which is my usual residual equation, and then I have this constraint equation which also involves delta u and psi delta f, and these two equations are coupled, right, because they both involve delta u and delta f, right. So, now I have to solve a coupled system, the combined equilibrium and constraint equations are then solved using a Newton-Raphson procedure. How do we do that? Well, let us see. Again, Newton-Raphson means linearization about the last converged state, right. So, again we write r plus delta r equal to 0, right. We assume that at my new, after I calculate my new update, my abscissa, it intersects the x axis, right. So, my ordinate is 0, right. So, r plus delta r is equal to 0, c plus delta c is equal to 0. Linearize that, delta r I write as del r del u variation delta u plus del r del xi delta xi, right, and this must be equal to, plus r must be equal to 0. So, the minus of this must be equal to r, right. Basically, delta r is equal to, just by linearization, right, is equal to del r del u delta u del r del xi delta xi. So, r plus this is equal to 0. So, this must be equal to r. Similarly, I do the same thing here, again I linearize del c del u delta u del c del xi delta xi, since c is a function of both u and xi, right. So, I can, when I linearize, I get this, and this is equal to 0, right. So, recall del r del u is equal to minus k, right, del r del u is equal to minus k, right. So, del r del u is equal to minus k because that is my tangent stiffness, and del r del xi is equal to delta f. Why is that? Well, let's go back and take a look. So, here we have our expression for r. If I take the partial of r with respect to xi, I get delta f, right. So, del r del xi is equal to delta f, right. And then if I denote del c del u by cu transpose and del c del xi by c xi, I get a coupled system like this. So, now I have k, which is this term, k delta u, right, k delta u, del r del xi, which is equal to delta f, right, delta f del xi, right, that is equal to r, right, and here I have del c del u, which I denoted by cu transpose, and here I have del c del xi, which is c xi. So, the cu transpose del u c xi del xi equal to c. There is a typo here, I am sorry, this should be c, right. So, that has to hold, right. So, let us look at the first equation, k delta u minus delta f del xi is equal to r, right. So, from this equation I can write del u is equal to k inverse r plus delta xi k inverse delta f, just by taking delta f delta xi to the right hand side, right, and then inverting k, right, I can get an expression for delta u. This is the typical condensation type operation, right. So, I get an expression for delta u which is k inverse r plus delta xi k inverse delta f, right. And then I denote k inverse r as delta ur and k inverse delta f as delta uf, and then I get delta u is equal to delta ur plus delta xi delta uf, right. The first term is the usual update, right. The first term is the usual update. Why is it the usual update? Well, it is just calculated by taking k inverse r like we did for the normal Newton-Raphson, right. That is the usual, and this is the contribution, this is the coupling term contribution, right. Because there is that coupling term, that is why I get this additional correction, right. The first term is the displacement sub-increment delta ur generated by the residual force r corresponding to that used by the Newton-Raphson method. The second term represents the displacement increment following from the adjustment of the load increment. If there was no adjustment of the load increment, then delta xi would be 0 and this term would vanish, right. But since there is delta xi is not equal to 0, I have this additional contribution, right. Delta u equal to delta ur plus delta xi delta uf. And then what do I do? Well, after I evaluate that, so this is typically the type of solution that we are talking about is very common and it is known as a condensation type solution, right. So, in the first equation what we did, we obtained delta u, we solved that equation to get delta u in terms of delta xi, right. And then once we wrote delta u like that, we are going to substitute that in the second equation, right, minus Cu transpose delta u. So, we are going to replace that delta u in terms of xi, and there is always a delta xi here. So, that will give me an equation purely in terms of delta xi, and then I am going to solve that equation to get my delta xi. So, using star in the second equation, I solve for delta xi like this, right. And once I have calculated delta xi, I again substitute that in this equation, I get my delta u, right. So, once delta xi has been calculated as above, delta u can be calculated from my previous equation, which was this, right. One thing one must note is that this equation, to solve this equation, is not that simple. Why isn't it that simple? Well, because all these, in case if I have a nonlinear constraint, if my c is a nonlinear function, of delta u and xi delta f, then I just can't solve it directly, right. I have to iterate, because every time I change this solution, these things are going to change. This Cu transpose this, that is going to change, right, because that depends on delta u and delta xi, right. So, that is going to change. So, I have to solve this equation iteratively. So, this system has to be solved iteratively. Again, iteratively means we assume some value of delta xi, solve for until it converges, iterate until it converges, right. For linear constraint, for instance, I have a hyperplane constraint, or for a quadratic constraint, I can get closed form solutions, right. That is, I do not have to iterate, I can just solve this equation in closed form, right, because then these things are no longer functions of delta u and delta xi, right, they become constants, right. In that case, I can solve that for delta xi directly, and once I have solved for delta xi, I can substitute it in my previous equation, solve for delta u. Okay. So, that was a very brief introduction to arc length methods. Arc length methods are extremely important, probably the only robust technique that can be used for solving a wide range of problems. wide range of problems, problems with limit points, problems with bifurcation type solutions when you have instabilities, things like that. Suppose in a typical civil engineering application, if you have buckling, right, when a structure buckles, right, there is an instability. Obviously at that point the load displacement curve changes slope, right. And if you are interested not only in knowing at what load a structure buckles, but you are also interested in knowing the post buckling behavior. You want to know the deformation patterns after the structure has buckled. In that case, Newton-Raphson is simply going to fail. It cannot work, right, because it's never going to converge. In that case, using arc length methods is a must, right. You cannot get anywhere, you cannot get any reasonable post buckling solution without using an arc length method. Several arc length methods are in use. For instance, the Ricks method, RIKS, the Ricks method is a common arc length method that is supposed to be one of the most robust arc length methods in use. Okay. So, that was a very brief introduction to arc length methods. Now, I want to switch to what are known as gradient based iterative methods, right. Look at the methods we have used so far for solving nonlinear equations. All of them are direct methods, all of them involve inverting a matrix, right, and finding the update, doing that over and over and over again until we get the equilibrated solution. So, that involves direct solution, it involves matrix inversion. Instead of that, we can use iterative methods, right, iterative methods for solving this system. Up till now, the methods we have considered for obtaining the solution update involve solving at each iteration the system Ki delta u n I equal to delta f for the Newton-Raphson method and the constraint system for arc length method. If I use the Newton-Raphson method, I solve this system. If I had arc length methods, I solve the coupled system, the constraint system. If Ki is a full matrix, then direct solution of this system by Gauss elimination or its variance is probably the most economical. If my stiffness, if my coefficient tangent matrix is a full matrix, right, then probably the Gauss elimination or any variance of those, right, those are probably the most economical methods. But in case those tangent stiffness matrices are not full matrices, right, that is they are sparse matrices. When we looked at Gauss elimination, we saw that one major problem with Gauss elimination was that during the pivoting process, which is of course essential for Gauss elimination in most problems, during the pivoting process it converts a sparse matrix into a more populated matrix, right, and as soon as it does that, it loses all the benefits of sparseness. It increases the number of computations, it increases the computation time, it becomes uneconomical, right. And we also saw that iterative methods are probably the preferred methods for problems where you have sparse matrices. So, that was for linear systems. The nonlinear case also the same holds. If Ki is sparse, then it may be more efficient to computationally to consider iterative methods, right, Any of the iterative methods we considered earlier, such as the Jacobi method, Gauss-Seidel method, or the successive over-relaxation method can be used. Alternatively, we are now going to propose something which we did not talk about before. Gradient based methods are widely used for sparse systems. We did not talk about gradient based methods till now because of their somewhat specialized nature, and also because gradient based methods naturally arise in the context of quadratic forms, which are by definition nonlinear. So, gradient methods are typically arise in solving what are known as quadratic forms, in finding minimum of a quadratic form, for instance, right. That is why we did not talk about gradient methods when we were talking earlier about purely linear systems, right. But these are very important methods for solving nonlinear problems, and one of the most important and one of the most probably the most simplest gradient based iterative method is the method of steepest descent, which we are going to talk about in some detail. The steepest descent method can be used to find the minimum of a quadratic form. What is a quadratic form? It is basically just a generalization of your simple quadratic equation in one variable that you are accustomed to, ax square plus bx equal to c, right? That is your typical polynomial, right? Quadratic polynomial of order 2, right? Quadratic general form is ax square plus bx plus c. Quadratic form is just a generalization of that to multidimensional vectors, right, to a multidimensional space. And how is that quadratic form written? Instead of ax square, I have this vector x with all these components 1 through n, x transpose ax, where A is a matrix, right? A is a matrix of size n by n, when x is a vector of size n, x transpose ax minus b trans, this is the quadratic term, this is my linear term b transpose x, and this is a scalar, right? This is a scalar. So this is just a generalization of a quadratic equation. And suppose we want to find the minimum of a quadratic form, minimum of a quadratic, what is the value of x which makes f a minimum, right? What is the value of x which makes the quadratic form a minimum? So that is a typical problem which is used in order to propose these gradient based methods, right? Later on we will see that gradient based methods are not restricted to quadratic forms. Quadratic forms are a special class of nonlinear equations, right? They're probably the simplest type of nonlinear equations, right? So we propose these gradient based methods, we discuss their properties in the context of quadratic forms because it is easy to understand, right? But we should always keep in mind that my real problem is probably never going to be a quadratic form. So I should be able to extend these methods, these gradient based methods, to general nonlinear problems, right, which are not quadratics, cubics, quartics, anything. That should work too, right? So if we plot the function f of x in n dimensional space for various values, now I'm concentrating on the quadratic form, right, the simplest nonlinear problem. So we are looking at steepest descent method, we are looking at gradient based methods in the context of the simplest possible nonlinear problem, which is a quadratic form. And we say if we plot this quadratic form in n dimensional space for various values of constant d, where d is equal to f of x, then we find each value of di corresponds to an ellipsoidal curve in n dimensional space. So if I consider if I have just two variables and I have a quadratic form, then I plot this quadratic form. Basically I plot f of x equal to d1, f of x equal to d2, f of x equal to d3. I plot for these various values of f of x, and for each value of f of x my quadratic form is an ellipse, right? Since it is 2D, it's an ellipse. In multidimensional space, it's an ellipsoid in that dimension, right? N-dimensional space, it's an n-dimensional ellipsoid. In 2-dimensional space, it becomes an ellipse, right? So in 2D, for instance, when x is equal to x1, x2, that x has got only two components, we get a series of ellipses corresponding to various values of di, right? So each of these ellipses correspond to a particular value of the quadratic. So along this ellipse, f of x is constant and is equal to d1. Along this ellipse, second ellipse, f of x is constant too and it's equal to d2, and similarly here f of x is constant equal to d3. And the problem that I am posing is that how am I going to calculate the value of x which minimizes, how am I going to calculate the values x1 and x2 which minimizes the function f of x, right? So if this, you can think of it like this, these are ellipses, right, and these are like contours, right? So, I am going to try to go to the contour with the smallest value, right, and that is going to minimize my function f of x, right. So, starting from some location, how am I going to reach the contour with the smallest value, right. Starting at a certain location, how am I going to go there? And we will see that one way to get there is to use the gradient. And what is the gradient? The gradient of a quadratic, which is just this, right, gradient of f and x in multi dimensions is del f x del x1 del f del x2 del f del xn, right. It is just a vector, n dimensional vector, each component is given by that. That is just your vector calculus, right. So, and if I take, and since I had f of x like this, if I calculate grad of x, right, if I calculate grad of x, I get half A transpose x plus half A x minus b, right, I get that, right. And if A is symmetric, what does asymmetry mean? We have talked about this many times before. It means A is equal to half A plus A transpose, right. There is no skew symmetric part. So, A is always going to be equal to half A plus A transpose, right. So, in that case I can bring out x and write this as grad of f x is equal to A x minus b, right. Just I am writing this taking advantage of the symmetry in A. Geometrically, the negative of the gradient is a vector that for a given location x points to the direction of steepest descent. It points to the direction where the function decreases by the maximum amount, right. So, at any point, let us go back to this picture again. So, I start from here, suppose this is my starting point, and I calculate my gradient, right. The gradient will always point in the direction in which f decreases by the maximum amount, right, and that in this case it is pointing in this direction, because f is going to decrease by the maximum amount if I travel in this direction in x1 x2 space, right. So, the gradient, the negative of the gradient is points to the direction of steepest descent, right, it points to the direction of steepest descent. Is a vector field that for a given location x in n dimensional space points in the direction of the greatest decrease, that means the steepest descent, right. It is like going down a hill, right. The gradient, if you are going down a hill, the gradient is pointing in the direction in which if you go, you lose the maximum altitude, right, you lose the maximum height, right. So, the gradient is the direction of steepest descent. Hence, when f of x has a minimum, gradient of f of x must be equal to 0. Why is that? Well, the gradient points in the direction of steepest descent, but when f of x reaches a minimum, is there a direction of steepest descent? No, right, because anywhere you go the function is going to increase, right, because that is a minimum, right. So, the direction of steepest descent has got to be 0 at that point, right, at the minimum. Direction of steepest descent I said is the gradient, that means the gradient got to be 0 at that point, right. And if A is symmetric and positive definite, since gradient of f x is equal to A x minus b, so that means at the minimum gradient of f x must be equal to 0. So, x minus b is equal to 0. So, in order to find the value of x which minimizes the function, I have to solve A x minus b equal to 0. Right. The minimum occurs when x satisfies A x equal to b. Up till now we were talking about quadratic forms. Quadratic functions, quadratic forms are nice well behaved functions. We will show later that they have what are known as global minimum, right. So, one point which is the minimum, it is a well behaved function with a minimum at a point. But in general, nonlinear functions do not possess global minimum, they possess many local minima. This can be considered seen by considering a 1D nonlinear function of x, right, g of x. If I plot that nonlinear function g of x, I have a function like this, suppose, and you can see that it has got multiple local minima, 1, 2, 3, 4, all of these are troughs, right. So, these are local minima, right. So, points 1, 2, 3 and 4 are all local minima of gx, and grad of gx is equal to 0 at all these locations, right. However, 2 is a global minimum. Why is 2 a global minimum? Well, you can see 2 has the lowest value of the function, right. 2 has the lowest value of the function. Since g of x of 2 is lesser than or equal to g of x for all values of x not equal to x2. Ordinarily, for an n-dimensional nonlinear equation, there is no algorithm which can guarantee that you are going to reach a global minimum. There is no numerical method that will assuredly converge to a global minimum. Convergence can at most be assured to a local minimum so long as the starting point is close to that local minimum, right. So, what does close mean? Close to the minimum means that the starting point is within the neighborhood when the convergence requirements of the algorithm are satisfied. Recall our convergence requirements of the Newton-Raphson method, right. We said that the Newton-Raphson method is assured to converge only within a certain neighborhood of the root, and in that neighborhood the function, the derivative of the function had to satisfy certain special characteristics, certain special properties, right. So, we are assured to converge to a global minimum only when we are within that neighborhood, right, within that neighborhood, and the particular local minimum the iteration converges to depends on the starting value of my iterate. For instance, if we start from A in the figure, if I start from A, if this is my starting point, I am going to converge to this local minimum 1. If B is my starting point, I am not going to converge to 1, I am going to converge to 2, right. So, the result I get from my solving my system of equations is going to be dependent on my starting guess, on where I start from, right. That is why it is very hard to get a global minimum, to reach a global minimum for a general nonlinear equation which does not have a, which is not a quadratic form. We start from A in the figure, we will converge to local minimum 1, while if we start from B, we will converge to 2, which it turns out is a global minimum, right, but we never know where to start from, right. So, nonlinear functions which are quadratic forms are exceptions to this general rule. They will always converge to the global minimum. This is because quadratic forms with a positive definite coefficient matrix A have the property that the minimum x obtained by solving Ax equal to b is not only a local minimum of the function, but it is also a global minimum of the function, right. Let us show that. To show that, let us evaluate f(x) at some arbitrary point p which is not a minimum of f of x, right. Suppose we evaluate the quadratic form at some location p which is not at my root, right, which is not at my minimum. At p, the quadratic form assumes this function value, and let us suppose that the minimum is given by x, which x is equal to A inverse b. So, we denote p is equal to x plus e, where e is an error term, because p is not equal to x, x is my true minimums, right, and p is not equal to x, I denote that difference by e, the vector e. So, I can write p is equal to x plus e. So, if that is true, then in this equation I can replace p by x plus e, right. If I do that, I get half x plus e transpose Ax plus E minus B transpose x plus E plus C. Expand this out, half x transpose Ax plus half E transpose Ae plus half x transpose Ae plus half E transpose Ax, right, plus half E transpose Ax, that is the last term, minus B transpose x minus B transpose E plus C, right. But half x transpose Ae is equal to half E transpose Ax if there is symmetry in A. If A is symmetric, then x transpose Ae got to be equal to E transpose X, that should be obvious, right. If it is a symmetric matrix, does not matter if I post multiply or pre multiply with E and X, right. So if I do that, then I have Fp is equal to half x transpose X plus that half E transpose Ae plus half x transpose Ae plus half E transpose X is basically just the previous equation. I have rewritten that just for convenience, right, and then I can replace, so half x transpose X, and I then bring minus B transpose X plus C, I collect those terms, and then I have half E transpose Ae, and since these two terms are equal, I can replace, I can sum them together and replace them with E transpose Ax, and then I have this term left which is this term left which is B transpose E. I have this term which is identical to that, right. I have this term half E transpose Ae, E transpose Ax, but I know that Ax is equal to B, right. So I can replace that with E transpose B, and then I have E transpose B minus B transpose E. So those two terms cancelled out, right. Taking dot product of E dotted with B is the same as taking the dot product of B dotted with E. Dot products are commutative, right. So these two cancel out, and I have left half x transpose Ax minus B transpose X plus C. But what is this? This is my quadratic form in X, right. This is my f of x, and I have this term remaining which is half E transpose Ae. But remember, we assume that A is a positive definite matrix, right. Positive definite matrix means that for any E which is not identically equal to 0, E transpose Ae got to be greater than 0, right. So this term is always going to be positive. So what does that mean? That if P is not equal to x, right, any P not equal to x is always going to be greater than f of x, right. Hence x is a global minimum of f, right, because this term is not 0, can never be 0, because A is positive definite, right, and E cannot be equal to 0 if P is not equal to x, right. So we are assured that a quadratic form or has a global minimum, right. So all these descent methods, right, they are going to converge to a global minimum. So we can use the steepest descent method to find x such that it minimizes a quadratic form. How do we use the steepest descent method? At any step in the iteration, we use the direction of steepest descent in the update formula. So I say that suppose I am at a location xi, right, and I want to any iteration, I have basic ideas, I am at xi, I want to go to xi plus 1. How am I going to get there? That is the whole idea of iterative methods. It's tell you how to go from xi to xi plus 1, and hopefully when you go from xi to xi plus 1, you are not going in the wrong direction. So you are converging towards the solution rather than diverging, right. So suppose I am at xi and I want to go to xi plus 1. So I am going to take the path which is along the steepest descent along the gradient direction at xi. So at xi, the steepest descent direction, the direction in which the function decreases by a maximum amount, is given by gradient of f of xi. So I am going to take a path, I am going to take a step in this direction, and the magnitude of the step that I am going to take is given by the scalar alpha. So I am going to travel in this direction, I am going to travel in this direction but the extent I am going to travel is governed by my step alpha. You can see that the step size is very important, right? If I take a very large step, suppose my minimum is somewhere here and I am somewhere here. If I am going in this direction, if I take a huge step, I will land up on this ridge, right? I will totally cross the minimum which lies somewhere here. So, I will land on the opposite ridge. You can think of this as a valley, right? And these as the ridges in a mountain, right? So, these are my two mountain peaks. There is a valley in between. If I want to go from here to the bottom of the valley, but if I take a very large step, I am going to reach the opposite peak, right? I am going to reach a point on the opposite ridge, right? So, the extent of the step I take is very important. So, the alpha, the value of alpha is very important. So, how to determine alpha? So, that is all it boils down to. How to determine the step size, because the direction we have to move we know that is the gradient direction. The steepest descent method, we move along the gradient direction, but how much should we move? Well, to determine that, recall that for a quadratic form, gradient of f of xi is equal to Ri is equal to b minus axi. We saw that earlier, right? Where did we see that? Or we probably did not see that, but it should be obvious to you. We did see that somewhere, but anyway, let us not worry about that right now. So, gradient of f of xi is equal to b minus a of xi, right, which is equal to, by definition, the residual, right, b minus axi. When xi is equal to x, then residual becomes 0, right. So, gradient of f xi equal to 0, we have seen that before, right, equal to b minus a xi, and b is equal to a of x, right. When I reach my minimum, that must be equal to a of x. So, I have a of x minus a of xi, right, and that if I write it like this, if I represent this as an error vector, right, x minus xi, I can write as a of ei. The step size, so this is just to calculate my gradient, right, the direction in which I have got to move. So, if I am at xi and I know my error, right, if I know my error or I know my residual, I can calculate my gradient, or I can just, but the amount by which I have got to move, the step size alpha, is determined by what is known as a line search procedure. And what does a line search procedure do? It tries to minimize the value of the function along that direction. So, I am at a certain point and I have a certain function value. I am moving along a certain direction and I want to travel, I only want to move along that direction to that point where I minimize the function value along that direction. So, this is a multidimensional space, I am taking a line in that multidimensional space. That multidimensional space, I only want to move to a location along that line where I get a minimum value for my function along that line. So, alpha minimizes f when the directional derivative d d alpha f of xi plus 1 is equal to 0, right. So, let us stop here for today. Next class we are going to continue talking about this. We are going to talk about directional derivatives, right, and we are going to find out how to do the line search, how to find the value of alpha, right. So, at least we can find the value of alpha in a, we can get a closed form solution for alpha for quadratic forms. For non-quadratic forms, no, that is not possible, right. There are other ways, other algorithms which can give approximate solutions, but not exact solutions for the step size alpha. So, we will look at that, then we will look at convergence criteria for the steepest descent method, right. What are the conditions which will allow the steepest descent method to converge, and this is all preparatory to talking about what is probably one of the most widely used gradient based methods for solving sparse systems, the conjugate gradient method, right. We are going to talk about the conjugate, start talking about the conjugate gradient method next class. Thank you.